for part 2. There we go. 11.8 lengths of curves. You already learned the basic form of this in your favorite Calculus 2 class. You know how to find the length of curve that is on the XY plane. And those of you who took the class with me had the project question to deal with no, did you have the project question or no? Yeah, you did, right? With the x squared thing? Yeah, perfect. I already forgot. All right. So what was the basic idea? If I have some kind of a function f of x, and I pick, and it's a curve, so I can't measure the length directly, and I pick a line segment, and I draw this triangle where I have change in y and change in x, and I have this little length L, this looks like a triangle. It's not a triangle. It's not a triangle because it is a curve, right? The alleged hypotenuse here is a curve. But you know what? For sufficiently small, it's close enough. So we can approximate the length between those 2 points with Pythagorean theorem. So now what we are going to do is we are going to use Pythagorean theorem and say that delta x squared plus delta y squared is equal to L squared. From where L is equal to the plus minus square root, but we can drop the negative because lengths are never negative. So it's going to be square root of delta x squared plus delta y squared. Then we are going to factor out delta x squared, and when it escapes the square root, it becomes delta x. Now, when you factor out delta x out of delta y, well, you just divide it by delta x squared. So, what I have here is I know. All right. So now you have delta x times, and we know from our calculus 1 that delta x is dx. So technically, what do I have? I have that this one length is the square root of 1 plus delta x over delta y squared dx, and we introduce the integral, because integral is going to say infinitely many of these very small lengths L are all adding together between a and b, forming our formula. Now, this is the formula, guys, that you know from your Calc 2 class. Otherwise, I need to update some grades. This is not new. You learned this in Calc 2. So here you go, Calc 2. And this is the length, right? Length equation. Now, length is one-dimensional. We always like to check dimensions to make sure that those dimensions match. So this equation has to be one-dimensional. If you look at this equation, the square root and the square counter each other, and you are left with the derivative. Integral and derivative cancel each other out, leaving the function behind, so you only have one function there, which is one-dimensional. So good. We do have, this is one-dimensional equation. We are all good. What is the big deal in Calc 3? Big deal in Calc 3 is parametrization. So we learned in, where? We learned at the end of the Calculus 2 parametrization, and we also learned polar coordinates. So we are going to now learn two different forms for this equation. One parametric form and then two polar form, so that we can compute lengths of curves when we are given those types of functions as the input functions. Now the cheapest one, the cheaper one of the two, is going to be the parametric one. Length of curve in parametric form. We start with a regular length equation we just derived. Let's write it as dy dx squared, Leibniz notation. And what I'm going to do is I'm going to multiply this by dt over dt. That's all I'm doing. So now I'm going to 1 plus dy over dx squared. I'm going to write dx over dt and leave dt alone. And now I take this dx dt and I undergo the square root, which means it will pick up the square. So I get integral ab. When this undergoes and multiplies 1, I will have dx over dt squared plus, and then I have dy over dx squared times dx over dt squared dt. dx's obviously will cancel, and we get L is a to b square root of dx dt squared plus dy dt squared dt, where a less equal than b. So here is your parametric form. And as you can see, it is the derivative of x in respect to t squared plus derivative of y in respect to t, and it's still under the square root. Now, if you want to, the length of curve can be also represented as f prime squared plus g prime squared of t plus h prime. So I'm extending this now for a 3D case where your good old R is FGH, each one of t, who cares? So it's such a subtle thing, but you see that this is actually the integral of the magnitude of the velocity. Do we see that? It's the integral of the speed, the length of the curve. They're all the same, whatever you want. Because it's your x and your y direction, which is these two. So this is the 2D case, this is the 3D case, and then because this is the square root of each one of these components squared, you can also compress it. So when I was learning this as a student, I remember this one over here. That's the one that I remember because I know what r prime is, and I know what the length is. So I know that that's gonna expand into this. I always learn. There should be a vector above it and a vector over there. Put in those vectors, guys. And girls. I had to. The one from yesterday I saw, I didn't see. All right, so there's our parametric form. Now let's use prove circumference of the circle. The formula for circumference of the circle of radius r, capital R. Well, prove the circumference of the circle. What's the formula for circumference of the circle? 2 pi r, exactly. Prove it using this, right? The length of the curve of the circle. For arbitrary radius. Formula for circumference of the circle, yes. 2 pi r. Yes. Yes. You know what the parameterization of the circle is, you differentiate, plug in, do the magic, and let's do it while we do it. My grandmother would say at least with head. What? Don't want to. Have a lot of lead?
Yes. Oh my god. They're awful. They're terrible.
And like,
They're nesting in the wall.
got this guy just like, they're nesting in the walls. Like that sentence just like killed her. They're nesting in the walls.
They're like attacking me in the video.
And they're plastic.
Yeah.
They get like this big.
But you know what?
They blend in our art is brown.
Then it goes so far.
I've had one on me.
Yeah. You don't feel the mission, right?
They're very gentle with their legs.
They actually don't. The only time you feel it is if they go into your nose.
I don't know where they're
Stop.
Real racquet player.
Stop.
Oh, really?
He's the worst person to tell my hair.
This is great. We're bonding.
No, it's not. I would never use it. In front of others.
I don't like this.
Send me one more.
I'm getting a C.
Alright, we'll explore that one. That's behind.
You can fill that one. So
Yeah.
now
You have one
that's not
ready.
why you got it. Chris is like Like these daddy long. Daddy long.
Yeah, I would never. I would never do that. But I would make it work. There's a Parametric movie.
There are so many harmonies, but
So you don't know Winnie? Winnie was our bio major, and he had the rose spider. French one.
Like that's what.
ah,
Yeah.
wow.
I used to have a video on my phone of Shannon Bowman.
I know. I've seen that.
Oh, you see that's really funny.
Yeah. Oh, we would make you do it too.
No.
If you were there.
Oh,
Ashley?
now I'm never, ever.
Ashley did it. Ashley was freaked out with spiders as much as you are. And I had a video and a photo of Ashley Wilson. The tarantula. Tarantula is as big as my hand.
There's not in my
And she Aaron gonna react.
No one was mentioning money, they did it just because they lost.
My hands are funny.
Yeah, tarantulas are furry. Well, it eats the little crickets, it eats people, you know, whatever it is. You know.
I'm not sure. But I could.
And there's a spider on his phone.
He just made it up like 2 seconds ago. I promise that's not.
No, I would never take a spider into or I would suggest, like I suggested,
Video of that. Just
it would be awesome.
Never go to Australia.
Bubble snakes.
I don't know.
I was trying to think of the one that's I came up to my vacation, and I'm trying to record a mom read it. It's
That's
amazing.
when you live in Australia.
No, I have like a garden site outside my front yard. Somehow it got in the house and it found a lake.
It's a garden spider.
Garden spider. Yes.
What's a garden spider? Yeah, they just.
No. She goes.
Yeah, something was spider.
Garden spider, and you are really sick out about spiders.
I'm really freaked out.
He's even sunbathing.
Sunbathing, sunbathing. Yeah. And spider looks like this.
Yeah, she made the most of it. That was actually just one leg.
Was this long? Wow, the tarantula that became without issues.
No.
Please Google it.
No.
A show?
No, mine.
I used to send a picture. I used to send a picture of the she never opened the phone.
I don't trust him.
They're cool. I think it's bigger, the less scary.
Yeah. They're like a dog, the furry. So the next test. Mary, see some.
Peeking out of a hole.
Yeah.
He's smiling. All right, let's take a look at this proof. You had enough time to try it. So the parametrization for the circle, we have a, that's not a circle. I need to use my superior drawing skills. So we have a circle. Why? Of radius capital R, whose parametrization is R cosine t and R sine t. And now what we do is we set up the integral. So input t is going to be from 0 to 2 pi because we want the whole circle around. So we go 0 to 2 pi, and then we have the square root of the derivative of the first one is negative r sine t squared, plus the derivative of the second one is r cosine t squared, everything dt. So now that is equal to integral 0 to 2 pi, and I have a negative squared is positive, so we have r squared. If you factor that, and you have sine squared t plus cosine squared t, which is 1. So you are integrating 0 to 2 pi r dt, which is rt computed through 0 to 2 pi, which is 2 pi r, and the proof is complete. So this is what it takes to prove that the circumference of the circle. So next time when you're tutoring a kid somewhere and test, so why is this formula so? There you go. So now you have the whole bunch of these. You just have to be, guys, very careful when you run into a problem that you cannot integrate. So you should be checking these problems using Wolfram Alpha or Mathematica, making sure that your integration went fine. All right, so the next part is to, or the last part, is to introduce the length of the curve in polar coordinates. We start with the parametric one, and we swap all t's with thetas, and then we fix it. So now, well, let's go step by step. So AB dx dt squared plus dy dt squared dt, t equals theta. So when we do that, we change alpha and beta because now the angle input. Dx d theta squared plus dy d theta squared d theta. So what do we gain from this? Well, we can still simplify this further because we have those equations that we covered in the last section in calculus 2, the derivative, so how to find the derivative of parametric of the in polar coordinates. So we know that x is equal to r cosine theta, and we also know that r is the function of theta. So to find dx d theta, we had to use the product rule. So copy the first one, which is r, and then times the derivative of the second, which was negative sine theta, and then plus cosine theta times r prime. So that means that this is negative f of theta sine theta plus f prime of theta. Well, next line. So dx d theta is given as negative f of theta, because r is f of theta, sine theta plus the derivative of the function times the cosine theta. So this gets plugged in here. Divided theta by the same concept. Y is arc sine theta. So it's going to be copy the first one, which is f of theta. Derivative of sine is cosine theta plus f prime theta sine theta. And this one gets plugged in there. Then you square them, clear all the common terms and all of that stuff. So I'm just going to say 3 dots, insert algebra here. Insert some algebra. There we go. And we get the length of the curve given in polar form, alpha, beta of the square root of f of theta squared plus f prime of theta squared d theta. Length of curve in polar coordinates. So maybe an example from the homework section. (36) Find the length of the spiral. R equals 4 theta squared from 0 to 6. Is that a sneeze? All right, bless you, whoever. Someone was trying to start a very long car. It worked out. I've seen it, but I'm like, no, fine, fine. My humor is more. We might never mention it again, actually, because it goes along with or actually, or it just becomes like a personal. My friend they kept like, no. Stuck on the derivative of 4 theta squared. I was concerned.
Next time. I'm gonna try it.
That's flattering. He actually cares. He doesn't care about a lot of things in here.
After the degree is all separate homes. So when she I got her a new job. We're terrible people. I don't know how it is. You know, I don't do that.
All right, let's take a look. So I hope you all got 4/3, open parenthesis, 40 to 3/2 minus 4 to 3/2, close parenthesis. If you got 7, it's wrong. All right, let's go. So we have that the function in terms of theta is given as 4 theta squared, from where we see that f prime of theta is 8 theta. The length of the curve is going to be from 0 to 6 square root of the function squared, which is 4 theta squared squared, plus the derivative squared, which is 8 theta squared d theta. So all we need to do now is a little bit of, whatever, black magic or whatever to solve this, and we're done. 0 to 6 square root of 16 theta to the 4th plus 64 theta squared d theta equal to 0 to 6. Now the trick is to see that you can factor out 16 theta squared, which leaves you with theta squared plus 4. And then this can escape the square root. Get 4 integral theta square root of theta squared plus 4 d theta. And now you can use u sub. So u equals theta squared plus 4, which means that du is 2 theta d theta. Since you have 4 in front, that gets cut in half because 2 is used up for d theta. Integral. So 2 theta d theta is du. We have a square root of u du. And then limits change using the formula. So let's do that here. I have u is equal to 0 squared plus 4 is 4. And u equals 6 squared plus 4 is 40. So the limits are 4 and 40.
2 times the integral, so u to the 3 halves divided by 3 and then halves, 4 and 40. And that's going to be 4/3 u 3 halves 4 and 40, which is 4/3 43 halves minus 4 3 halves in parentheses, and that's going to be some decimals afterwards. So that's it. So that's the length of the curve. If you want to know how this curve looks like, what you should do is you should go and graph it on the Wolfram Alpha or calculator, or use the middle school method to check the points, and that takes care of it. All right, so that's 11.8.